Instrumental methods of analysis. In this lecture, we will learn some thermal analysis methods.
First one is thermogravimetry or thermogravimetric analysis. So thermogravimetry, thermo means with heat, by process of heat. Gravi represents the measurement of weight measurement, and metry is the analysis. So analysis by weight measurement with the process of heating is what is called thermogravimetry or thermogravimetric analysis. So thermogravimetric and gravimetry is a technique in which a sample is continuously weighed as it is heated at a predetermined and preferably a linear rate. So you are linearly or continuously you are heating the sample in a rate. You are increasing the heat and you are seeing what is the weight difference in the sample. That is what is done here. And the weight change, what weight change is happening in the sample is plotted against temperature. And you are getting a curve. And from that curve, you can get several informations regarding the thermal stability of the compound, the composition of the compound, the composition as well as thermal stability of the intermediate compounds also. Like if the compound is decomposing to give another intermediate compound, you can know about the thermal stability and composition of the intermediate compound and the composition of the residue also. So the simplest diagram is this. Suppose you have a compound A which is in the solid form, which is being heated and which on heating decomposes to B, another solid, and a C gas is evolved. So when the C gas is evolved, there is a change in weight. So you are plotting the weight on the y-axis and temperature on the x-axis. So you can see this flat region, this represents the compound A which is being heated. So till the temperature reaches here, there is no weight change. When temperature reaches this point, it is decomposing to give B and A gas. So there is a weight change as temperature is being increased. And at this point, at this temperature, the decomposition is over and you have got A as completely converted into B, and you have the B remaining here, and the B is stable along this temperature. So in all the plots, usually there is a horizontal portion. Horizontal portion represents no weight change, and the vertical portion represents a difference in weight. So that's all is there in these graphs. From this, you can get informations regarding its composition, its thermal stability, the original compound as well as the intermediate. So for example, you can take an hypothetical compound MX2 2H2O. 2H2O is water of hydration, and it is, suppose it is heated. So when it is heated, from A to B on the curve, the sample is stable. You can see from A to B on the curve, the sample is stable and there is no weight loss. At B, the sample begins to lose weight because it is giving off water of hydration, 2 moles of water. And the process will be complete when temperature reaches C. Temperature, when it is C, you are getting the anhydrous MX2. Now it is not the hydrated compound, now it is the anhydrous MX2. Now the anhydrous MX2, it is being continuously heated in a given rate. Again, further temperature is increased along CD, there is no weight change. That is, it is stable in this temperature. And when it reaches D, the sample begins to lose weight, and it may be due to the decomposition of MX2 to the oxide. And when the point E is reached, it is stable. This is the EF is the stable curve of the oxide. So AB is a stable curve of the hydrated compound MX2 2H2O. BC represents conversion of MX2 to H2O to MX2, the anhydrous form. CD represents the stable curve of the anhydrous form. DE represents the conversion of the anhydrous MX2 to oxide, and EF represents the stable curve of the oxide. So it is an example of a real compound which is TGA of calcium oxalate monohydrate. So calcium oxalate monohydrate, when it is heated, this is the curve that you are getting. Calcium oxalate monohydrate, CaC2O4 H2O, when it is heated. So in this curve also you are seeing several flat horizontal portions and vertical portions representing its transformation into different intermediates. And you can see from the figure, calcium oxalate monohydrate is stable up to 100 degrees centigrade. This is representing calcium oxalate monohydrate. And from there, it is getting converted to the anhydrous form. So it is losing a water molecule. So in this portion, it is losing a water molecule. And now it has been converted to the anhydrous calcium oxalate. Now this is stable up to 226, from 226 to 398 degrees centigrade. In this portion, this is stable. And when after 398, it is getting decomposed into the calcium carbonate and carbon monoxide. So here, what is in this portion, what is getting evolved? You can see carbon monoxide is evolved. The weight is shown here. Initially, the calcium oxalate taken was 2 milligrams. In this portion, the weight change was 2.46 milligrams, which is representing water molecule. In this portion, the weight loss is 3.85 milligrams, which is representing carbon monoxide. After carbon monoxide is evolved, then you have the calcium carbonate there. So calcium carbonate decomposes to give calcium oxide and carbon dioxide. So this portion represents stable curve of calcium carbonate. And in this portion, calcium carbonate is getting converted to calcium oxide and carbon dioxide is evolved in this portion, which represents a mass change of 6.02 milligram. And after that, this represents the stable curve of calcium oxide. So this is stable curve of the hydrated monohydrate calcium oxalate. This represents loss of water. This represents stable curve of the anhydrous calcium oxalate. This represents loss of carbon monoxide. This represents the stable curve of calcium carbonate. And this represents the conversion of calcium carbonate to calcium oxide, and with the loss of carbon dioxide. And finally, this represents the stable curve of calcium oxide. Now we will see some instrumentation part of it. So the main components of the instrumentation part is recording balance, a furnace programmer or controller, a recording device, a balance control. So this is giving the weight change to the recorder. This is giving the temperature to the recorder. And the recorder can get both the values of the temperature as well as the weight, and it can plot it along the x-axis and the y-axis. Here the balance is very sensitive, and here on one side you have the sample. In this figure, this is how it is shown. Here you have the sample container, and depending upon the weight loss in the sample container is kept inside the furnace. It is taken inside the furnace, and depending upon the weight loss in the sample container, this pan, it will go up or down. And here you have a reference.
Initially, without the sample, the instrument is adjusted to 0 reading or null reading, and then the sample is kept
and it is heated, and with reference to the reference, you can see what is the weight change. It is given to the recorder. And here you have thermocouples for measuring the temperature of the sample. So we will see the different components. The recording balance, this is the most important one. So it should have the following characteristics. It should record continuously the weight change of the substance as a function of temperature and time. It should record the temperature to an accuracy better than plus or minus 1 degree centigrade. It should be able to adjust the range of weight change. Even small weight changes, it should be able to adjust. And it should have a high degree of mechanical and electronic stability. And the heating rate should be linear. Linear means it should be a steady rate and it should be reproducible. So every time you do the measurement, it should be the same heating rate, and it should cover a wide range of temperature, that is up to 2000 or more degree centigrade. So these are some characteristics that it should have. And you have the furnace. Furnace is so constructed to allow an easy access to sample holder. So it should be such that you can keep the sample in it and you can easily insert it into the furnace. And it should be able to cool rapidly also after carrying out the experiment. Then the furnace design and control should maintain either a linear heating program or fixed temperature. Whatever type of adjustment is needed, it should be able to do it. Whether it is a linearly heating or you are keeping the temperature as fixed. The control is done by placing a thermocouple closer to the furnace winding. So usually the furnace, if it is heated by coil of wires, windings, then the thermocouple for the temperature of the furnace is kept near the winding. Now, high temperatures can be obtained by using graphite tube furnace. And for the winding, nichrome winding and platinum rhodium winding can be used for temperature of 1000 degree to 1450 degrees centigrade respectively. So depending upon winding, you can have the temperature also. And the thermocouple, which is kept near the sample, it has to measure the temperature so that we can plot the temperature versus weight loss. And suitable thermocouples may be used for measuring the different temperatures. And for up to 1100 degrees centigrade, the choice of thermocouple is chromal or aluminum thermocouple. Chromal and aluminum are alloys. Chromal contains 90% nickel and 10% chromium. Aluminum contains 95% nickel, 2% aluminium, 2% manganese, and 1% silicon. And if you want up to 1750, then thermocouple made of platinum alloys and rhodium can be used. And if you want still higher temperature, tungsten or rhenium thermocouple can be used for measurement. And you have a recorder. Recorder records the weight loss and it gives the output in the form of an XY graph. On x-axis, you have the weight change and y-axis, you have the temperature. I have shown the one diagram for calcium oxalate monohydrate. Now, there are certain factors that affect thermogravimetry. The two factors are instrumental factors and sample characteristics. So we'll first come to the instrumental factors. So first one is furnace heating rate. So the effect of furnace heating rate is to decrease the decomposition temperature with decrease in heating rate. For example, it is given that if heating rate is 5 degree per minute, the temperature for 10% decomposition of polystyrene in nitrogen atmosphere, it is 394 degree centigrade. But if you decrease the heating rate to 1 degree per minute, then the decomposition temperature decreases to 375 degree centigrade. So depending upon the heating rate, if you reduce the heating rate, the decomposition temperature also decreases. The recording chart speed also is an important factor. Furnace atmosphere, what is the atmosphere inside the furnace is important. For example, calcium carbonate decomposition takes place at much higher temperature when it is carried out at an atmosphere of carbon dioxide than if you take nitrogen as furnace atmosphere. If you have a reaction like A solid equilibrium giving B solid plus C gas. Suppose it is an equilibrium. Now, if the atmosphere in the furnace has the same gas that is evolved during the analysis. Okay, so you know the Le-Chatelier's principle, the equilibrium will shift towards the left. If you have the same gas in the furnace, then since this is a reaction which is at equilibrium, the equilibrium will shift towards the left. So in such cases, it will affect the reaction. But if you have a reaction like A solid giving B solid plus C gas, here it is only in one direction. It is not a reversible reaction. In this case, if you have the same gas C in the furnace, then this won't be affected during the analysis. Now, if you have A solid plus B gas giving C solid plus C gas, if you have a reaction like this, and if the composition of gas B is changed, then the effect on the reaction will depend upon nature of the gas in the atmosphere. If you have a gas which is reacting with A, like oxidizing gas or the reducing gas, the TG curve will be affected. So these are regarding furnace atmosphere. Then geometry of the sample holder is also affecting. A flat plate as well as a deep crucible are usually used. Shallow dish is widely used because of rapid exchange of gaseous material. So depending upon the geometry also, the curve will be affected. Then you have composition of the sample container. Depending upon what sample container you are using, the curve will be affected. Now next is sample characteristics depending upon the sample. Now amount of sample. If large amount of sample is taken, then there is a deviation from linearity, and especially this is for fast and exothermic reactions. For example, in the reaction where calcium oxalate decomposes to give calcium carbonate plus carbon dioxide. This is a fast exothermic reaction. So in this case, the amount of sample will be affecting.
Amount of sample is also important if we want to detect the intermediate compounds.
So if we want to detect the presence of intermediate compounds, then it is better to use small samples. For example, if you want to study the thermogravimetric study of copper sulfate 5H2O, here if you are heating the 5H2O, the water of hydration is getting removed. So 5H2O can become 3H2O and then it can go to the anhydrous form. So if we are taking 1800 milligrams, then it won't show the formation of copper sulfate 3H2O. But if we are taking 0.426 milligrams, then copper sulfate 5H2O getting converted to copper sulfate 3H2O, our intermediate will also be shown. Then comes the anhydrous copper sulfate. So the amount of sample also is important to detect the intermediates. And solubility of the evolved gas in the sample is also affecting. And particle size is also important. Particle size will alter the rate of reaction and the shape of the TG curve. So as particle size decreases, the decomposition temperature increases. Sample packing and nature of packing also is affecting. A closely packed sample will decompose only at a higher temperature compared to a loose packed sample. Then comes heat of reaction. Heat of reaction means any heat evolved during the process, evolved or absorbed during the process. If there is some heat evolved during some exothermic reaction, then the sample temperature will be ahead of the furnace temperature. It will be more than the furnace temperature. On the other hand, if it is an endothermic reaction, the sample temperature will be lagging behind the temperature of the furnace. So it will be lesser than the furnace temperature. I will just show a small video.
Thermogravimetric analyzer TGA 1000 and 1500. TGA is a method of thermal analysis in which the mass of a sample is measured over time as a function of temperature change. Results provide information about physical phenomena such as phase transitions, absorption, adsorption, and desorption, as well as chemical phenomena including chemisorption.
And you can see the sample is kept and furnace is going up. So when the furnace is going up, the sample is going inside the furnace.
Thermal decomposition, and solid gas reactions. The Infinity Pro software is used to control and record data, as well as analyze results from the TGA instrument.